Okay. Today we're going to talk about Linux security and the Chromium Sandbox. And there's actually going to be code in this presentation. It's going to be C, mostly. If you don't feel comfortable with the C, just wait for the pretty pictures. So, who am I? My name is Patricia. I have been a consultant for a little while. Consultant in, well, I haven't really started the consulting part. But I started a company. I started a company, and I started working for the company in the summer. And I'm mostly spending my time learning stuff and speaking an incredible amount for some reason. I am a self-identified C++ programmer. It's okay. I'm okay. I have worked on 2 browsers. The most recent browser I worked on was Vivaldi, and I worked also on the original Opera browser. In between those 2 browsers, I worked for Cisco making embedded telepresence systems, and I was also a short stint a Java programmer for NUUG. I've worked mostly in C++ since I graduated, but during my studies, I programmed mainly in Java. I can program in many languages, though, except C#, which is on my to-do list. Okay. So, before we get started, it's kind of important to know that browsers are in the remote code execution business. The whole purpose of a browser is to download random code from the internet and execute it on your machine. And it's kind of nice to have that as a mental model, because then you kind of know the area in which browsers are working. So to try to make this concept of executing random code more safe, the concept of sandboxing has grown. And this has been more of an organic process that has been occurring since early 2000s up until now. And it has a lot to do, and it wields, to a large extent, platform APIs that are available from the different operating systems, and also that kind of functionality has also grown organically from the different operating systems. And sandboxing itself is mainly concerned with an external threat. So the idea is that you have some kind of threat which is external to your physical machine, somebody out there, you know, the famous hooded hacker. But it also is starting to deal with system internal threats. And this is a little bit like the rest of the security industry that has been largely focused on perimeter security, and now is starting to focus more and more on detecting something within your network. We're going to talk mostly about the system external threat, because that is mostly the focus of browser security, although there has been some work in the second category. So the outline of the talk is we're going to look a little bit at the process architecture of Chromium, specifically on Linux, because this talk is about Linux. Then we're going to look at different Linux security APIs, then how the initial sandbox is built, and then the final shrinked sandbox. So to actually understand how the Chromium Sandbox is built on Linux, you kind of have to understand how the Linux startup process, or the Chromium Linux startup process is, because it's built as the browser starts. So if you look at a Chromium-based browser, then you will see some executable files on your file system. So I'm basing this on Vivaldi, but it's basically any kind of Chromium-based browser. So you have Chrome, you have Vivaldi, you have the new Opera, you have Brave. Many different browsers are based on the Chromium project. So you will have some kind of, you will have 3 executable files. The first one will be the name of the browser generally, and in Vivaldi's case, it's called Vivaldi. It's a bash script that sets up some initial stuff. Then you have the actual binary, and then you have another binary, which is the setuid binary. But it's not that much used today, and we'll get into the reasons why it's not that much used today, so I won't talk about it much, but it will come up on occasion. So when you start up the browser, like as you notice, there's only one browser binary. But when you look at your computer, if you do top or PS or something, or when you're wondering why you have no more RAM, you'll see lots of processes, right? But you only saw one binary. So this one binary is actually constituting many types of different kinds of processes. So when you start up the browser process, it will spawn a child process, which I call Zygot init, but we'll look at how it looks on the command line later. Zygot init spawns another child, which is called Zygot. And this one is the one that produces all of the renderer processes. Now, a renderer process will be roughly equivalent to a tab. It's not equivalent to a tab. There's like lots of details about exactly what will constitute making a new renderer process. But that is the general idea. Also, you will find a GPU process and a GPU broker process. So when you see these running processes, if you do PS, you will see them have a little bit of a different command lines. Like the actual browser process will be launched without this type parameter. Whereas both of the Zygots will have this type Zygot. And the renderers will be type renderer. Those are the ones that you will see many of, right? And GPU parent will be called GPU process. And the broker, which is a child, will be called GPU broker. There is currently, last time I checked at least, a bug here, which means that the word GPU and GPU broker is gone. So it is currently called dash broker. I should probably submit a pull request. Anyway, moving on. Yeah, so that's the general idea. So you have an idea on how all of these processes just come into existence. One of the things that's important to realize is that there is only one binary, so you kind of have to re-execute the same binary to create all of these different processes. And we're going to look a bit at that as we go along. But the Linux security APIs that we're going to be looking at, we're going to start by seeing how you can see them on your machine. So if you go to your browser, your Chromium-based browser, of course, and you do, in this case, Chrome://sandbox, but whatever browser, Chromium-based browser will have this. And you will have this nice little box. You won't have this nice picture, but you should. And then in this box, you'll have different kinds of things. So the first one it says is red, and it says SUID sandbox. And that was the other binary that I said that we wouldn't talk that much about, but keeps coming up. Yeah, so basically we're not using that. And the reason why we're not using that is because of the second one. We're using what they call the namespace sandbox. And the namespace sandbox is basically available if you can create a user namespace as an unprivileged user on this distribution. Now, this is true on many of the big distributions today, for example, Ubuntu. And so if you are able to create a user namespace, and we'll come back to what that means, then the rest of it will generally be green. And so it will say, do you have a PID namespace, network namespace, seccomp BPF sandbox, seccomp BPF sandbox supports tsync, and Yama LSM enforcing. Now, you don't have to understand any of this, because by the end of the talk, hopefully you will. OK, so we start with this. This is the web. We have a web page. It's inside of a renderer. So this little circle is like our little renderer process. And so we are going to create a network namespace. So you can consider that some kind of like enclosing thing so that this process inside cannot escape this little bubble. For a network namespace, by default, that basically means you have no network access. So this little like red dashed arrow means no access. Then we create a PID namespace, and a PID is a process ID on Linux. And if you're in a PID namespace, you can't see the other processes. You kind of think you're alone, and you also get a fake PID. So if you're the first process in a PID namespace, you get PID1. And this is the reason why I call the Zygot process Zygot init, because Zygot init is PID1, and it behaves like an init process. An init process is a specific term on Linux, which is basically one of the first processes that started, at least before we had System D, and we don't want to talk about that, but which is in charge of reaping all sorts of other processes. But anyway, that's, yeah, it's not important for this. We also create a user namespace, and a user namespace is really cool. A user namespace is basically, we're putting this process inside of a user namespace, and so it will be owned by, well, if you create it by default, it will be owned by root. And when I say root, I mean it's not really root, but the process thinks it's root. So the process thinks it's root, and the moment you think you're root, suddenly you have access to all sorts of APIs that you didn't before. And that's the reason why you have to have this possibility of creating a user namespace unprivileged. Because if you can create a user namespace unprivileged, then inside of that user namespace, you are privileged. It's a neat trick. Anyway, moving on. We'll go more into detail on this as we go. I just want to give you a high level. So different kinds of APIs that are in use are like set_rlimit, which will limit access to different kinds of resources. And then we will use chroot, which I have a tendency to call chroot because I didn't know how to pronounce it, and now it's like that in my head. Anyway, and we're going to use chroot to limit access, or actually cut off access to the file system. And finally, seccomp and capset to limit access to system calls. All of this is basically to try to isolate this web process, or this renderer process, right? And the reason for that is the sandbox concept is actually based on the idea that you have escaped the browser. Because the sandbox is not really useful until you have a browser escape. The idea is that, let's say that you have somehow managed to escape the browser and you managed to execute code on the machine. The idea is that whatever kind of context you are in should be really boring. You will have basically no fun stuff to do. And so all of this setup is basically to make the world that this process sees as boring as possible. So moving on, we're going to look a little bit on how those APIs are used when you create the initial sandbox. So the most important thing, like I said in the beginning, to remember is that there's only one binary. So we have to re-execute it in different ways as we set up these processes. And one of the things that is important is that this architecture wasn't really meant for security. This architecture was made by Google when they took in the WebKit project. And the reason why they did it this way is because when they took in the WebKit project, which Apple was developing at the time, or they still are, but Google forked it after a while. But at that time, they were sharing. The problem is it was developed in-house at Apple. Apple dropped it once a night. It was very unstable. Google was not happy. And so they created an architecture which basically put this web engine inside of its own process, and then if it crashed, they would just start a new one. They marketed this when Chrome came out as, you can only crash a tab, you won't crash the browser. Of course, the reason why this was a thing was because it happened a lot. But anyway, but the cool thing about this architecture, and the reason why it became really popular with other browsers as well, which is how you see multi-process Firefox coming, is because the moment you have many processes, you can use system APIs and system capabilities to do some of your sandboxing in isolation. And so that's what we see here. So first, the browser will make the Zygote init, which is PID1. It's called Zygote init because it's basically just standing around just waiting for all the children. But it does that with a clone exec. Now I'll talk a little bit about what that means. And it will create this child in a user PID and net namespace. Then Zygote init will create its child using fork, and Zygote will make its child using clone. I'll talk a bit about what fork and clone means. And then the GPU process is created with fork exec, and then the GPU broker is created with fork. And so the initial sandbox is creating just the first 2 children here. Okay, so what is fork exec? This is something that you will see Linux people talk about a lot, like, okay, we did a fork exec like it was a thing. But a fork exec basically is how to create another process and execute a program in that process. Fork is a system call where you create a copy of your current process, including all of your virtual address space, and there's copy on write and all sorts of stuff. But anyway, so you basically have 2 processes which are executing the exact same program and are in exactly the same place. Both of these programs will, after you call fork, return from fork. And in the parent, it will get, as a return value from fork, it will get the PID, that is the process ID, of the child process. And the child process will get 0. If you ever look on any example of fork, this code is like the standard thing. You have to figure out if you're the parent or the child. And the whole concept is to try, what am I going to do now? But if you join that up with an exec, what you're doing is, yes, you've created a new process, but you're saying you want to execute another program in that child process. So instead of being a copy of me, I want to do something else. In this case, actually, when you do a fork exec in terms of Chromium, you're saying, I want to make a copy of me that's running the same program, but I don't want to run it exactly like this, so I just want to start over. So it does an exec of its own binary, the same binary. But what happens when you do the exec is basically you start from the beginning again. So now you have options. You can send in command line parameters. You can tweak your environment. You can do things like that. So you will generally see that when you create a new process, you will have this fork exec. Now, clone is a bit different. It's very similar because, in fact, fork is often implemented using clone. But clone is much more low level and has much more like fiddly interface. And we'll look at uses of clone a couple of times in this presentation. Yeah. So the most important thing to understand is there's no such concept as a sandbox. And other thing that's also important to understand is that these same APIs that I present here are also used for other things, specifically a lot for containers. So Docker, things like that, they use these APIs in the same way. And that has actually been a lot of the process for creating these APIs in the OSs has been the emergence of the cloud and containers. But anyway, so there's no such thing as a sandbox on Linux. There's no such thing as you can say, make a new sandbox. Instead, a sandbox is something that is just constructed by calling different kinds of system calls to set up your process in a certain state. So sandboxing opportunities, if you only use fork, are very small. You basically have before you call fork and after you call fork. It's not very interesting, but there are some things that you can do. But it becomes a little bit more interesting when you do a fork in an exec, because you have, again, what you do before. So you basically have some preparation you can do before you actually call fork. And things you might want to do is like close unused file descriptors, stuff like that. Because things like that, they leak over to the new process. So you can sanitize as much as you can in your own virtual memory before you copy it over to your child. And that might be something you want to do. Then you have @clone, and we'll look at that later if you use clone. And then you have before you exec. So after you forked, so you've created this child, and you've both forked, so you've returned, so you have a child and a parent, and they're sort of in the same place. If in the child, then you can say, okay, I want to do an exec, but before I do the exec, because when you do an exec, you have to pass the command line, you have to make the environment, things like that. Now you can pass different kinds of command line arguments to your child. which is a way of passing messages to this new process. And you can also sanitize your environment or set new environment variables, lots of other stuff. And then at startup, when you've been exec'd, you can make certain choices based on your input. But we're going to primarily, in this first part, look at the first two. And that's when namespaces come in. Now, I've already talked a little bit about namespaces, but basically, a namespace limits what a process can see. And that is the isolation part. It doesn't limit what you can do or the resources that you have access to. If you want to do things like that, you can look at C groups, for example, which is also widely used with Docker or other types of containers. And it is also like C groups. We're not going to, I have a slide on it at the end, but I don't think we'll look at it because it depends on the time. Anyway, but basically, namespaces limits what you can see. So you think there are only a few users on this. You might think you're root. You might think that there are no other processes running, things like that. You might not have any access to the network. The primary API that is used to create a namespace is clone, and it is then when you make a new process. There's another API that is used once, which is called unshare, which puts the current process in a new namespace. Yeah. So the namespaces that we're going to look at are these. I already talked about them a little bit. So you have, and these capital letter things are the flags. So they're called this, and we're going to pass them in the call to clone. And I'm going to show you how that looks. So you have clone new user, clone new PID, and clone new net. And we're going to create them as it's interesting that it's kind of cut off at the end, as we create the namespace. So the flags that you pass to clone define how the child will be created. And this is kind of interesting because clone can do many things. One of the things that clone is used for is to make threads. And that kind of shows you exactly how versatile it is. A thread is created passing a whole bunch of clone flags, but amongst those clone flags is, for example, share address space. So from the kernel's point of view, a thread and a process are not that different. But inside of Chromium, the difficulty of making a browser is that it has to run on a lot of very diverse hardware, very many different distributions that have different capabilities. And so you will see inside of Chromium a lot of testing and to see if something works. One of the most important things about this is to understand that you can have your browser running on 2 or 3 different distributions, but it doesn't mean it's sandboxed the same. Basically, your browser will try to see what is available and use how much it can to create the best sandbox it can, given what it has. So it will test what namespaces are available. It will fail if it's not sufficient. If it fails, it will usually fall back to using the setuid sandbox, so the one that I said I wouldn't talk about. And yeah, and then it will construct the best it can. But it has a really interesting use of long jump. I am a C++ programmer, so what I think is interesting are usually painful things. It's an occupational hazard. But anyway, so long jump is basically something nobody's actually used for like 15 years. But it is interesting the way it's used here. Yeah, and so this is the code. We're going to start here. So the most important thing, I guess, to understand about long jump is that it is sort of like a long distance go-to. It's like a go-to is generally a way to jump from one place in a function to another place in a function without like Anything? A long distance go-to is you're basically setting dynamically, programmatically a label somewhere, and then later you can go to it. And it can be in a totally different function, far down the stack. So that's what we're doing here. So the jump buff with the env buffer here, the jump buff env is something that is allocated on the stack. It will store lots of current information about the current running context. So that means that when we do our long distance jump to go-to to this jump buffer, then it can kind of start where it was. Yeah, so we do set jump to set like, okay, I'm setting my label right here. And then we're passing in this buffer, because this buffer can later then be used to jump to. And it calls this function clone and long jump in child. And I did not make this up. This is the Chromium way. They like long sentencey names. But the thing is, the reason why I find this technique very interesting is because it's basically, when you program, people often think you're programming computers, but very often you're programming communicating to other programmers. And this is definitely one of those cases, because the thing is, clone is not a very widely used API. Most programmers have never seen it in their life. But most Linux programmers have seen fork. So the whole concept here is to try to emulate fork so that clone isn't so scary. So in this case, you're going clone and long jump in child. So this is a call to clone. And now you can see a little bit why clone is kind of clunky. It takes a lot of parameters. Fork takes none. It's really nice. You have int fork empty param. It's like, there's hardly a way to do that wrong. But this one has tons. And one of the weird things is you even have to pass in the memory used for the stack. This is very like do-it-yourself kind of thing. And so what you should pay attention to is, of course, we had the flags earlier, which was the clone new user, clone PID, clone new net. And we're also creating the stack. But the first parameter to clone is this clone helper. Clone helper is a function. And that is the weird thing about clone. Instead of, like in fork, you have the parent and the child, they both kind of return from fork, and they're just like, haha, nothing happened. In clone, the parent will return from clone, and everything's fine. The child will execute this function. So the child will execute this clone helper. And so to be able to emulate this as a fork, it uses this jump buffer. So basically, when you call this helper function, if you look down here at the yellow parameter, this env, we're passing in this env to clone. And this parameter will be passed to the function. So this void star is this env, this jump buffer. And then we reinterpret cast, which is like, the reinterpret cast is basically a C cast, but C++ developers don't want to talk about it. But we basically degenerated to just trust me, okay? It is what I told you. And then we do a long jump, which we're basically jumping to this buffer, this little label we said earlier, which basically means we end up, here again. And so the parent will return from the clone call, and the child will return from the set jump. It's kind of weird. But basically, this means that you can put it into a function that emulates fork. It's just like weird little Linux APIs coming up. Anyway, moving on. Unshare looks like this. So you can have unshare and then pass in the namespace you want to use. And then this current process moves into this namespace. It doesn't create a new process. And this is used in this function can create process in new user namespace. And again, this is one of those testing things, like what is available on this platform? Will I error out somehow? Okay, then we look at the second part. So before exec, there's a lot you can do. I'll just rapidly list up a couple of things or a bunch of things, and then we'll look at a couple of them. So you can fix your environments. And that's a lot you can do there. Fixed file descriptors, that's very interesting because you might want to make sure that a bunch of file descriptors that are sensitive files or maybe pipes or things like that, that you can close those. And then you have signal handling, because what happens if you get a segmentation fault or an interrupt or something, you know? Set of process groups, resource limits, but this one we'll look at a little bit. Set no new privs. It's like a really, really small call, but it's really important. And then you can change the current directory to maybe be someplace else, and then you choose the executable path and the command line. Okay, so we're going to look at a couple of those things when we look at shrinking the sandbox. So this is kind of now added a lot of detail, and we go through this new box. But basically, what is important to note here is that we have created these two children, right? We created the Cygot init using clone, and we created the GPU process using fork. One of the things that's important to note then is that since we created the GPU process using fork, we didn't actually create any namespaces. The GPU process is a highly trusted process in Chromium. It runs basically with full-out privileges on your machine. And the reason for that is it communicates with your GPU driver, it loads lots of graphics libraries, and these need a lot of privileges to your machine. Okay, moving on. So, PR set no new privs. This is a mitigation that was introduced in Linux years ago to try to limit the possibilities of a process to do privilege escalation. Basically, when you set PR no new privs, it basically means that whatever privileges I have right now, and privileges capabilities is a Linux concept, but basically says you can't have any new ones. You can reduce the set you have, but you cannot in any way, by making child processes, by doing XX, whatever you do, there's no way that you or any of your children can get anything more than what we have currently. And it's done very simply like that. Yeah, so if it is set, like I said, they will these operations that would try to elevate your privileges will fail, or it won't grant them. And this is very important because it's a prerequisite for seccomp, which we'll come back to now. Okay, so seccomp is really cool. Seccomp is actually a repurposing of something that was in Linux already. There was a mechanism, a little virtual machine in the kernel, which has been there for ages. And it was used to filtering of TCP packets. And the reason why you wanted a little virtual machine in the kernel to do your filtering of your packets is because if you wanted to listen or look at packets, it was very expensive to pass them over the user space kernel boundary for each packet, because there's a lot of traffic. And the overhead for passing that boundary is very large. So to limit the overhead, you only wanted to pass packets you were actually interested in. And so they made this little virtual machine inside of the kernel, and then you can install a little filter program in that little virtual machine, and that would filter your packets. Very cool. It's been there for ages. But the thing is, with this little virtual machine, is basically it can execute a little program. This we can use for other things. And this is where seccomp came from. So seccomp is used widely in Chromium to do filtering of system calls. Because seccomp grew out of mostly like the container business, also from sandboxing. The idea that you don't want this process to be able to do all sorts of system calls. So how are you going to do that? And basically what seccomp does is that you make a tiny little program that you install in the kernel, that whenever this process makes a system call, this little program will run and check if this is acceptable. And seccomp can filter on many different things. So you can filter on which system call, but you can also filter on what the parameter values are. And you can even choose how to react. So you can fail in all sorts of ways. You can exit the process if you want to, but you can also just have a soft failure. You can just fake it. You can do all sorts of things, which makes this very powerful to control this API between the kernel and the process. So inside of Chromium, this is implemented. Yeah, well, it is an assembly-like language. It's really not developer-friendly. This is basically bytes, and the best the default API for this is like a bunch of macros. It's quite horrible, actually, but you know. Like Linux isn't like that. It's not like soft and cuddly. It's more like prickly. So yeah. Anyway, so it runs in this little VM. And if you remember from the beginning, we had this little box where if you did chrome://sandbox, and it said seccomp supports tsync. Tsync means that if you install a seccomp filter in this process, it applies to all threads. Now, it's kind of weird that it didn't, but this was like a new feature, so you kind of have to test for it. Yeah. So inside of Chromium, seccomp is implemented as classes. There's a bunch of classes that generate these programs. And the program is defined in some kind of policy class. Inside of the policy class is basically like a really thin wrapper around a switch. So it's basically a switch. It has a switch inside of it, and it will switch on which system call. And then you can choose how to react. The main point here is that if you fall through the switch, you fail. It will abort. And that means that this is a whitelisting technique. That means that if you do anything not in the whitelist, then it will fail. And if you subclass a policy with your own switch, then that will be an extension. You will have just a longer switch. It will go through the parent switch and your switch. And so it's basically any kind of extended policy is more permissive. And the hierarchy is basically like this. So you have a baseline policy, then you have a GPU process policy, which is a child of that, and then GPU broker process policy, which is a child of that, and then render process policy, which is unrelated to the GPU ones. Okay, so basically you do this. This is the code. Looks really like nice and high level C++-y. You know, you make a sandbox, you start the sandbox, and start sandbox, you install filter. Of course, I've removed all comments and logging and error checking because, you know, it doesn't fit on the slide. But anyway, this is what it looks like, real life. All the names are real too. Anyway, but it degenerates quite quickly and install filter. Because basically, it just kind of, okay, let's just generate this bytes that we need for this program. Then we need to install it, and we basically do that by copying these bytes into a buffer and then passing the buffer pointer to the buffer into the kernel. So it's like you start off with something like nice, high level and fluffy, and then the whole thing just goes to just like C and Linux and poof. Anyway, moving on. So then we have another cool thing. It's chroot. I'm really trying not to say chroot. Anyway, so this one is quite famous, mostly for like jailbreaks and stuff. But in this case, it is used to cut off access to the file system. And it's done with this really cool technique. And I'll show you the code, but basically it is like this. So you use clone call again, but this time you use another type of flag. You call clone fs. Clone fs is clone file system attributes. And two of the things that happens with that child is that now it's supposed to share file system attributes with its parent. And that means that if they change directory, they change together. Like if one does change directory, they both change. Or if one does chroot, both does chroot. The reason why this is very interesting is, and I can show you in the next one. So it's going to do chroot to a specific directory, and you can see this directory if you do this ls -l proc and then the pid and root. You can see this directory. Okay, anyway, moving on. Yes, so it calls this function, and here's what I said. You have this clone file system, and then you have this Linux sig child just to make sure you get proper signaling. And if we go into this function that the child is going to call, which is this chroot to self fd info, very like explicit naming in Chromium. Anyway, so, and this is it. Now the thing is, it looks very small, but this is quite interesting, because this is the function that is called in the child process. So you've cloned a child process, you're sharing file system attributes with your child process, then your child process does chroot to /proc/self/fd info. Now this self word here is very important, because this is a process-specific directory. It is a process-specific directory to the child process. Then we do change there to /. We have now both changed the chroot for both the parent and the child, and we have changed directory for both the parent and the child into a directory which is process-specific to the child. And then the child exits. And this directory no longer exists. And the parent is now not in touch with the file system anymore. It's kind of cool. Anyway, so then you have capabilities. I'm going to go very quickly through that, because it's not that much fun. Capabilities on Linux is a kind of broken system. Because basically you kind of need capsysadmin for anything, and then you have everything almost. So capabilities was a way of trying to do this kind of segmentation of privileges on Linux, but it never really worked. But what I have to say is they use, like all of the browsers, they will use all of the APIs. Even the ones that are kind of sucky, it's like, yeah, well, it's like, it can't hurt. So it will do to drop capabilities as much as it can. And it does this in this function called credentials drop all capabilities. This is the cygots and the renderers will basically go like, take away all of my privileges. And then you have resource limits. And then here you have an API called setRlimit. And it's used very limitedly. So it will do setRlimit AS, which is the address space of the process, and rlimit data, which sets the maximum size of the data segment. So basically, if we want to recap, these processes have no access to the file system. They've also been very limited by seccomp. They've been limited by capset and the chroot. And they are now in this weird space where they can't see other processes. They can't see other users. They have no access to the network. This is very interesting, because these renderers are the ones that are actually rendering the web page, right? They have no access to the internet. For the renderers to get data from the internet, they have to have it piped from the browser process. So the network stack is in the browser process. And it has to pass forward that over using shared memory to the renderers for them to actually render the web page. But the funny thing is, the renderers can't actually render anything to the screen, because they don't have access to any kind of graphics drivers. So they have to pass whatever they made over to the GPU process to even put anything on the screen. Okay. Anyway. So we looked at this, and now you understand a little bit more what this box says. Except, of course, the last one, which is the Yama LSM. That is not really used in Chrome Desktop or Chromium Desktop, and it's only checked. But this is more for this sideways protection for internal threats, where a process running on your machine might be able to dump the memory of your process. And there's a lot of interesting tidbits in the memory of browser processes, you can imagine. So this talk has been largely based on Chromium and kernel source code. Linux man pages a lot. LWN.net, and Michael Kursik's absolutely infamous book, The Linux Programming Interface, which is basically the Bible for programming on Linux, and also his several courses of his. And that's my talk. Thank you very much. Any questions? Yes.
Thanks. I was wondering, how does WebAssembly fit into this picture? Can you explain that?
Okay, how does WebAssembly fit into this picture? That is a kind of difficult thing. WebAssembly will be largely executed inside of the sandbox. So you will have the code generation as you would normally there. As far as I understand, on most browsers, this is true. You have virtual memory that is used for passing information. But currently the thing is, the problem with WebAssembly currently is that it's sort of like in a standstill because of the whole Spectre meltdown thing. A lot of central features were turned off. But it's coming back. And so, yeah, it's kind of a difficult thing. And it's still very much in development. But I was thinking maybe, okay, this is, okay, user thing. Would people be interested in a talk on how, like, implementation of WebAssembly in browsers? Like, hands up? Okay, a little bit, okay. Because this is something I've been thinking about. I've been talking about one of the people working on it on Firefox, and I was thinking maybe I'd do it. Okay, yeah. Okay, any more questions? Yeah, I'll repeat your questions just to go.
So this information was largely, was mostly based on Linux. Do you have any idea how if the same concepts are implemented, for example, in Chromium for Windows, isolating file system, network, etc.?
Okay, the question is, are the same types of mechanisms available on or used on Windows and or Mac, I assume? Yes, but the thing is, this code is totally platform specific inside of Chromium. So there are only like very high level APIs that they share, and that is because it is very platform specific what you can do. So I haven't looked specifically a lot at Windows. I looked a little bit on Mac on how the sandboxing there works. But it's basically the same types of things that they try to do. Same types of isolation. So yeah, I would assume it is very different, very functionally very much the same, but implementation-wise totally different. Yeah. Okay, with second BPF, is it a good idea to run user-supplied code in the kernel? That is specifically what it was made for. And so the reason, it has a lot of constraints. So you only are allowed to have, I don't remember how many thousands of instructions. You can never do jump back. You can only jump forward, so there's no looping that you can do. So it is very limited in what you can do to make sure that you cannot DDoS the kernel. But the reason why they chose it is, of course, that it has a long history. It's been tested a lot. It's been studied over a very long time.
There was a breakout in it recently, wasn't there?
There's been a couple, especially the idea here is that if you can somehow turn it off, that is the golden thing. If you can turn off the seccomp that has been installed, the seccomp filter that has been installed, then suddenly you can do whatever you want. So yeah. Yes? How was what? Oh. So, you guys are hard. Okay, how was the rowhammer attack implemented in JavaScript? I don't know. Maybe that should be another talk. But yeah, a lot of those kinds of attacks are based on getting some kind of reading from some other place. And basically that is also what you saw was like the whole Spectre meltdown idea is that that CPUs in general leak information. And if you are able to read it somehow, then suddenly all bets are off. And no sandboxing in the world will help you. Which is the reason why it was a big deal. But it's also the reason why it's sort of like applications kind of just throw up their hands, because it's very limited what you can do about it. Because this is a hardware issue. Yeah. Oh, that's interesting. Is the sandboxing code easily reusable for something else? Not really. Not really, but at the same time, it's fairly separated also, because it is very platform specific. It's not really messed in with all of the other code because it's basically in platform specific files mostly. But Chromium isn't that good at like co-locating stuff, so that it's often like spread around, so you kind of have to pick it up from different places. Yeah. Yeah.
I can follow up on that because recently Cloudflare launched their new Cloudflare Workers, which is a function as a service thing based on the Chromium project. So could you comment on that? Is that a good idea, or how should we start on this?
Gosh. Okay. The question is, how do I feel about Cloudflare's new function as a service? I like the fact that we went over to functions as a service. Can I say that? You know, the whole serverless thing. It was just okay. Anyway, I mean, this is a problem with cloud in general, right? There are levels of security. And you have to decide exactly how safe you need to be. Like, are you on a multi-tenant system? Then if something manages to break out, then there is memory there, right? There's stuff around that might be interesting. And those are the kinds of things you will also see with Spectre Meltdown. Is like the container boundaries can be crossed. But I mean, it's probably better to like, with regards to mitigations for those kinds of things, the cloud vendors have been really, really proactive. So generally, they are the first people who are patching their systems. So it really depends. Sorry. Yeah, any more questions? Okay. Yes, thank you.